Welcome to undergraduate pilot training. This academic lecture will familiarize you with the basic navigational concepts in Star Citizen. This academic course number is BA100C and is a part of the basic aviation module of the instruction in the undergraduate pilot training syllabus. It is a requirement for the UPT certification. In this presentation, we will briefly cover the mechanics of celestial navigation, how we orient ourselves on a planetary body, and the standard navigational systems used in Star Citizen. Let's begin by very briefly reviewing the concepts of navigating the stars and how those concepts are used in Star Citizen. First, a quick review of spherical coordinate systems. Similarly to a Cartesian coordinate system, or X, Y, and Z, spherical coordinate systems are also based in three measurements to describe a location in three-dimensional space. However, these systems use different reference components than Cartesian systems. The first component is some sort of origin point. The second component is some sort of fundamental geometric plane that contains the origin. This fundamental plane defines 0 degrees of latitude. The third component is a primary direction lying within the fundamental plane. This primary direction defines 0 degrees of longitude. Perpendicular to the fundamental plane and passing through the origin are the poles, which are the definition of 90 degrees latitude. Spherical systems can be oriented in a left-handed or right-handed circular convention, although the vast majority are right-handed. Which brings us to the coordinates themselves. The three coordinates used to describe the location of something in three-dimensional space using a spherical coordinate systems are longitude, latitude, and range, and in that order. This is likely different than what you are used to hearing. In this example, we will use a right-hand system. First, we measure the longitude in degrees, minutes, and seconds of arc from the primary direction. Remember that a right-hand circular convention measures counterclockwise, as depicted here, following the natural curve of the fingers of the right hand. Second, we measure the latitude in degrees, minutes, and seconds of arc from the fundamental plane. Lastly, we measure the range from the origin in a straight line to the object we are locating. This brief review of spherical coordinate systems is fundamental to understanding the various celestial coordinate systems available to us because all of them are spherical. There are 5 systems in use in astronomy based on the scale of the frame of reference. In lieu of describing each system's origin, fundamental plane, and primary direction, we will focus instead on their usage. The horizontal system is used to locate and navigate around on the surface of the Earth. The equatorial system is used in earthbound astronomy, such as telescopy from the Earth's surface. The ecliptic system is used in location and navigation within our own solar system. The galactic system is used in location of objects within our galaxy. And finally, the supergalactic system is used in the location of galaxies within the observable universe. Each of these celestial coordinate systems have their own associated problems with variation when describing a celestial position, and each variation is unique to that system. Because the horizontal system's primary direction is rotating with the Earth, any horizontal coordinate for the position of a celestial object will only be correct at a specific date and time and only from a specific location on the Earth's surface. Because the Earth wobbles, or in other words nutates, slightly around its rotational poles, each equatorial coordinate will vary as the fundamental plane, Earth's equator, also nutates with it. Therefore, any equatorial coordinate must also include a time epoch to define when the coordinate was accurate. Our solar system is located on the Orion spur of the Sagittarius arm of the Milky Way galaxy, which is also spinning. As we travel past other galactic objects, our gravity and their gravity interact. These gravitational interactions cause variations in our relative velocity within the Milky Way, and these variations are termed perturbation. Again, any ecliptic coordinate must include a time epoch to define when the coordinates were measured, so compensation for perturbation can be calculated. Lastly, we do not know what variation exists in the galactic and supergalactic coordinate systems due to the fact that we cannot get a sensing device such as a telescope out to a great enough distance to properly observe galaxies as they move, or the entire universe writ large. It is a safe assumption that some sort of variation exists, but we will likely never know what they are with any certainty. So, which system does Star Citizen use? Based on the scale of Star Citizen's play area, which is star systems connected by jumpable wormholes, the logical choice is to utilize an ecliptic coordinate system. Horizontal and equatorial systems are too small scale to handle navigating an entire solar system well, and galactic and supergalactic systems are way too large scale for what the persistent universe is doing. However, the official ecliptic coordinate system only exists in, and therefore is defined by, the Sol system. Each stellar system in the persistent universe would need its own custom ecliptic system, but this is not problematic as the developers can quite literally build each star system as they see fit. And this, in fact, is what they have done. Each star system has its ecliptic coordinate system's origin point at the center of the star or barycenter for any multi-star systems. The developers located each planet's orbit within a single geometric ecliptic plane, therefore defining a fundamental plane. They then arbitrarily picked a primary direction, as the scope of this decision requires no applicability outside of the simulation itself. Once we have those three items defined, the rest falls into place. 90 degrees up and down from the ecliptic gives us the poles, and we can now start using longitude, latitude, and range to position everything in the system, including ourselves. The circular convention is also an arbitrary decision, so since the real-world ecliptic system is right-handed, the developers have also implemented a right-hand convention. But wait, we discussed the problem of perturbation earlier. What about that? Again, the power of the developers comes into play. So now that we have the system for navigating within the persistent universe star system, how do we navigate around planets and moons? That is a great question. Obviously, we need to start with the cardinal directions, but how are those determined? The answer is again the right-hand rule from earlier. If we imagine taking our right hand and relaxing it so that the four fingers form their natural curve, then we imagine laying our cupped hand on the equator of a planet with our curved fingers lying in the direction of its planetary spin. If we raise our thumb, the thumb points in the direction of the North Pole by convention. This is literally the definition of the North Pole of any spinning planet or moon. And if you have north, you have south. East is into the spin and west is anti-spin. And to help with navigating our way around a globe with a spacecraft, we have a standardized system of nav points around any celestial body known as orbital markers. Each planet or moon has 6 orbital markers known as OMs surrounding it at key points. All of these OMs are geostationary and co-altitude from the surface. OM 1 and 2 are special as they are always over the poles. OM 1 is over the North Pole, OM 2 is over the South Pole. OMs 3, 4, 5, and 6 are all distributed at 90-degree intervals over the equator. OMs 3 and 4 are opposite each other, as are OMs 5 and 6. Therefore, this is what the moon Lyria would look like. So remember, OM1 is north, and the sun always rises in the east. Now that we have all the conceptual constructs, let's dive into the practical use of the navigation systems in the spacecraft we fly. First, we need to familiarize ourselves with the different symbols our nav system displays using augmented reality. Planets are displayed as a circle, moons are a small circle superimposed on a larger circle. Lagrange points and comm relays are marked with a small diamond, while orbital markers are marked with a similar diamond that is 25% larger. Space stations are annotated as a rounded square. On the surface of a planet or moon, a major landing zone or city is marked as an upside-down home plate, and any other surface outpost is annotated by a hexagon. If the outpost or landing zone is on the other side of the planet or moon, that is denoted by the symbol being drawn with dashed lines. If the path to the nav marker is clear, the nav marker will be in the same color as the spacecraft manufacturer's HUD color. If the path is blocked, then the symbol will be displayed in red. To quantum travel, or QT for short, to a nav marker, we utilize a 3-step process. First, a short tap on the Bravo key starts the quantum drive spooling and displays the navigational HUD. Observe the spooling indicator counting up at the top of the navigational HUD. Next, aim the bore sight cross at the desired nav marker. The navigational calibration indicator will begin counting up, displayed to the left of the navigational HUD. Last, once both indicators are indicating spooling complete and ready, respectively, long hold the Bravo key to engage the quantum drive and jump into QT. There are two methods for choosing a destination for quantum travel. If a route has not been set in the nav system, spooling the quantum drive displays all nav markers in the local area at once. This can make for a very cluttered HUD and can also prove difficult to aim at the desired nav marker if another nav marker is occluding it. However, if short jumps around the local planetary system is all that is desired, this can actually be an expedient way of navigating. However, a desired destination can be selected in the Skyline Mobiglass app, and Skyline will calculate the most efficient routing from the current position to that destination. If that route is then set, only the next nav marker in that routing is displayed in the HUD. Also, this selected nav marker is displayed persistently across all HUD formats, so it can be referenced even when the navigational HUD is not displayed. Additionally, the Situational Awareness Display, or SAD, displays a pointer line to the selected nav marker. To set a route in Skyline, first press F2 to open Skyline. Selecting a destination will display information in the upper right corner along with a range to that destination. If the destination selected is correct, then press Set Route at the top of the screen. Routing information will display in the upper left corner. Verify that the route legs make sense and that the fuel required is less than the current fuel on board. The nav block info is worth a closer look. The route legs and the fuel each leg will consume is numbered and displayed in this space in the info block. A small circle over a downward triangle at the left of the leg annotates the current leg. Quantum fuel planning is summarized at the top of the block. It displays the current fuel on board and the sum total of the fuel required for the entire route. At the bottom of the nav block is a horizontal rule. At the left of the rule is a sum of the route legs and the number of route legs completed, displayed in a 3 of 5 type format. At the end of the right rule is the estimated time en route to complete the entire journey, displayed in seconds. To summarize the major takeaways from this presentation, OM1 is always the North Pole, OM2 is always the South Pole, OMs 3, 4, 5, and 6 are over the equator. Nav markers in red are blocked. Dashed nav markers are on the other side. F2 is the shortcut to Skyline. Make sure you have enough fuel before you jump. And finally, tap Bravo to spool, aim at the marker to calibrate. When spooled and ready, long hold Bravo to jump. That completes this presentation of BA100 Charlie, Basic Navigation Concepts. The next lesson is BA100 Delta, Basic Communication Concepts. If you have any questions, contact your instructor pilot to get them answered. Thank you.